And there turns out there is a method that'll do that. It's called the ritz or the Rayleigh-Ritz method. And the Ritz method utilizes a quadratic functional inferred from the weak form of the equation. So, and it turns out, I mean, we're getting closer to the finite element method here. So it turns out that the finite element method is just a piecewise implementation over finite elements of the Ritz method. Right? So as of right now, we're still talking about a continuous thing. We haven't discretized it yet. Right? So we can use the Ritz method on continuous bodies, but it has some limitations. And so we're going to talk about this for the rest of today and maybe a little piece of next time. And then we'll get into, finally, we'll discretize the body, and we'll have finite elements. And essentially, the finite element method is the piecewise implementation of the Ritz method over finite elements. Okay? So to develop the weak form, we have a three-step process. Okay? And I think I mentioned to you earlier that a lot of people teach finite elements. They start with this sort of matrix methods and structural mechanics, and then later. But the reason I do it this way is I want to show you that it doesn't matter what the ODE or PDE is. You can solve any boundary value problem with the finite element method. And if you have the strong form of the equation and you follow these three steps, it doesn't matter what the equation is, you can develop the weak form. And then you use that to solve it. Okay. So the first step, it's a very, very systematic three-step process. It always works. Okay. So the first step is the same as the weighted residual method. So we're going to have our model problem. I'm going to say C of x is equal to 0 because it doesn't really add anything to this. Right? This is just an extra term I have to carry around. All right, so that's just restating our model problem. There's our differential equation over this domain subject to these boundary conditions. So the first step is to move everything to one side of the equation. Okay? So move everything over to the left-hand side, multiply by a test function, and integrate over the body. All right, so I'm going to move everything over. So move everything over. All right. Multiply by a test function. Integrate over the body. Step 2 is that I'm going to I have an integral. I'm going to integrate this first term by parts. Right? So I'm going to, I'm going to distribute the test function. Right? So if I'm going to multiply that by that and that by that. And then the first term, I'm going to integrate by parts because I have this d dx over here. So this is like this thing. If you go back to our integration by parts formulas, it's like this thing is v, and this is w, right? And I'm just going to then apply the integration by parts formula. Right? And what that's going to do is it's going to get that differential off of this term, off of a v, and shift it onto that. Right? But then I have an extra boundary value term that pops out over there too. Right? So I'm going to integrate by parts. Okay. Now, can anyone, we're developing a weak form. Can anyone guess why we use the word weak? As opposed to this guy, which is strong. This is, strong form. Why is this the weak form, or what? Like you hit it. We weakened the continuity requirement on U, on the solution, right? So there, right, we have d dx, and then if we distribute that, we have d squared u dx squared. So to solve this equation, our solution has to be a continuity such that you can take two derivatives of it, right? This guy, though, we've shifted one of those differential requirements onto the test function. So now our solution only has to be continuous. It doesn't have to be continuously differentiable. It only has to be continuous so that one derivative exists, and of course then our test function has to be continuous. So one derivative of the test function has to exist. So the third step, and I'll write it down on the next page, but I just want to point out, the third step is to apply the boundary conditions into the weak form. So look at this term. Does that look like that? At least at x equal to L, right? So what is that equal to? So I can just put L right there, at least at x equal to L. At x equal to 0, I'd evaluate this at x equal to 0, but remember what we said, at x equals 0, the test function can't be arbitrary. It has to conform to the essential boundary condition. So the x equal to 0 term actually goes away because of that, just like what we talked about last time. So step 3 is to impose the boundary conditions. So you remember when we talked about the names of the boundary conditions, the essential and the natural? And I sort of pointed it out. There we started with a quadratic functional, and we minimized it. And you saw that the boundary condition was sort of in the quadratic functional. Here we're going to go in the other way. We start with the strong form, develop the weak form, and you see that the natural boundary condition just goes in there. So this is really a huge advantage of the finite element method over some other methods, is that the natural boundary conditions just naturally fall into the weak form. And so they're just, when you construct the solution of this guy in the discrete solution, you just sort of don't have to do anything. They're there. They're just part of the equation. So this is the weak form. Also known as the variational form.